how to characterize marine compounds. I just want to show you what exactly is infrared spectroscopy at first, and then we will move on to how we will move on to the section that how it is going to help us identify the marine compounds. So first and foremost thing is that I just want to tell you that what is an electromagnetic spectrum and why it is important. So, every wave that is present in the universe, it all falls in the category electromagnetic spectrum. The reason being, it has both electric and magnetic properties. It's very simple. So any wave, you take UV or you take visible light, you take infrared, microwaves, X-rays, gamma rays, they all have both electric and magnetic properties. And so IR is again classified into three different types: near infrared, far infrared, and mid infrared. So it is an electromagnetic wave. Okay, so and if you look into the table, that the first one is a gamma rays, X-rays. So they are high intensity radiation, and followed by infrared and the microwaves and radio waves and so on. Okay, the thing is, the type of transition that will happen with the high intensity radiation varies with the drop of low intensity radiation. For example, X-rays, gamma rays, when passes through an object, it does nuclear and electronic transition. So it is high intensity radiation. And if you take radio waves, because it's a low intensity radiation, and that's the reason it is not doing any type of electronic transition, rather than just make the molecule to vibrate. And the near infrared and the infrared, all these waves, it's not an high intensity radiation nor a low intensity radiation. So it will just make the molecule to vibrate, and we measure that vibrational frequency. Okay, so that is called vibrational spectroscopy. And like I mentioned, so it is divided into near infrared, far infrared, and mid infrared. Okay. Yeah, so high intensity radiation, the thing is, you have to remember, high intensity radiation causes electronic transition, and low energy radiation causes vibrational and rotational transition, which will be useful for us because we are going to use IR as an wave in this particular equipment. Okay. Yeah, so what is the type of molecular vibrations that will happen? It could be a stretching vibration, it could be a deformation, it could be, bending, rocking, twisting, wagging. So different types of vibration will happen. These are all the vibrational modes that will happen when an IR light passes through. So it's basically, what is the, the molecules, how it is interacting with your electromagnetic wave, whether it is, moving in this direction, whether it is moving in this direction. So it is, this is the categorization of the modes. Okay. And if you take any basic spectroscopy, it will have these components. It will have a light source, it will have a laser reference, and it will have interferometer and a sample compartment where you will keep your sample, and detector, which will be there in the equipment, and the processing unit, of course, is a computer, and you will get the output as a printout or as a graph. Okay, a spectrum basically. Yeah, so this particular equipment is present with us. It is available with us in our lab, and it's from Shimadzu IR Affinity 1S. So this is the diagram outline. And so yeah, like I mentioned, these are all the vibrational specific specific to a molecule. For example, if it is OH or NH, it will come here in this particular region in 3200 or something like that. And if it is C double bond O or C double bond N or C double bond C, it will fall in 1700 to 1600 region. And likewise, so it varies with different groups. And if it is a C O or CC or CN, a single bond, it will probably you can find it in this region where we call it as a fingerprint region in 1200 or 1500. So in this region, so these are all general absorption frequencies, which is commonly, this you can find it anywhere. You can Google it and you will find these results. But when you know your samples better, it will be useful for you to identify an exact group. For example, this OH, if it is a stretch, we can find a strong broad band between 3200 to 3600. And likewise, the same way for alkane and for alkenes, and amine, aromatics, CC, ether, nitro, carbonyls, aldehydes, amides. So this you can Google it and you can find it. So it's not a big deal. Yeah. So these are all the basic components present in the FTER. It will have an interferometer, and what an interferometer does is that it basically has a beam splitter. This equipment will have a beam splitter which will split the beam into two, for example. Sorry. Yeah, it will split the beam into two, and what happens is that one half of the beam will move towards a fixed mirror, the other half will move towards a moving mirror, and it will when it hits the fixed and moving mirror, it comes back, and when it falls with the same path, it is split into two, and when two waves superimpose on each other, that's where interference is created. It could be a constructive interference or destructive interference. In constructive interference, you will find a wave. In destructive interference, you will not find a wave. You will see a dark band, and we only take the constructive interference. That's the wave that you will get. Maybe I will show you. Yeah. So this is what happens when two waves superimpose on each other. You will find the constructive interference here and the destructive interference. Okay. So yeah, here this is the constructive interference and this is the destructive interference. Yeah, so and you may all wonder that so it's basically infrared spectroscopy, and why we call it as a Fourier Transform infrared spectroscopy. So the reason is that, and I hope you all would have seen someone playing piano. So if you take this key, this will have a different frequency when on comparison with this particular key. Okay, here. So this key, if you click, you will hear a different sound when you compare with this key. So each and every key produces a different frequency, which is unique to the key itself. Okay. The same way, if you click all the key at a single time at a given point, you will hear a bang, but it has all the frequency. So we may not be able to detect that all the frequency, and that's the reason we use Fourier transform to make that sound noise to be elucidate to give a meaningful spectra. So this is what happens. It basically converts a time domain to frequency domain. So that's why Fourier transform is used. Okay, so you usually get a single peak like this. You take any spectra, you will get a peak like this here. Okay, and it is Fourier transformed to get a meaningful spectra like this, which we can read as an output. You take any sample, you run it in FTER, the equipment will only give a single peak like this. Okay, so it has all the meaning, and when you Fourier transform it, you will get a power spectrum like this. So this is further correlated as infrared spectrum. So that's the reason we call the equipment as Fourier transform infrared spectroscopy. And what are all the types of sample that you can run? The thing is, you can do solid sample, you can do liquid samples, you can do films, resins, paint. Almost you can do all the samples except with samples which do not have, except with samples which have water. Okay, if water is there, it will interfere with your results, because water peak will show up in regions like 3200 and 3600 region. So you have to be very careful with that, and so that is one concern that you should look. So this is just an example of n-octane, how you will get a spectra in FTER. And what are all the window materials for solid samples? So if you have a powdered sample, like for example, if you have a pure compound, if it is in powdered form, you can use pelleting, KBR pelleting technique, which is a window material where it does not have any active region in the infrared spectra. So that's the reason we use potassium bromide or NaCl. And you can also use diamond, sapphire, quartz, or something like that. So these are all the available window materials, but in most cases we usually go for potassium bromide or sodium chloride. So these two are commonly used. And FTR can be very useful in comparing a reaction between before and after the reaction. For example, if you really want to check what has happened to a reaction, or what has actually caused the molecule A to converted into B, then you can do a before and after reaction, and you can check what are all the groups involved in the change of A to B with the help of C. Okay, so I'm just giving an example. So this is a spectra that that was run before the sample, before the reaction of a sample. Okay, you could see the spectra like this. You observe a spectra like this, and when the reaction is completed, the same sample gives a spectra like this. So now if you have to look closely into the groups, whichever groups has actually made a change in the shift, in the wavelength shift, which means that when two molecules are placed like this and IR light passes through like this, either the bond stretches or it bends. Okay, we measure that frequency, and it is it is unique to each and every a chemical component. For example, C and C will have a different bond when you compare with C and N, and likewise O and H. Okay, so each bond will vibrate in a different frequency when IR light passes through. So we measure the vibrational frequency. So that will be useful to study before and after reaction. So that is one thing. And what are all the types of detectors available? It is there in the equipment itself. You're not going to have a look at it, but I'm just giving you an example. So in earlier days, there was only thermocouple detectors, pyroelectric detectors. Okay, so now the technology has improved a lot. Now we are going to see DLA-TGS, deuterated L-alanine doped triglycerine sulfate. So it is a very sensitive detector, which can give you the output in a very specific manner. It is the result will be very specific. And yeah, you can do solid and liquid samples like I mentioned before. And yeah, and water is a big enemy to this equipment. So we have to keep all the spare parts of this equipment in a desiccator. Okay. So there is an auto dryer mechanism is present in our equipment that we have in our lab. It basically converts a water molecule, try to enter into the detector, and it converts it into hydrogen gas. So that this setup is there. And these are all the characteristic amide vibrations. It will be useful for biologists who are mostly working with proteins or enzymes, who will be looking for amide 1 and amide 2 groups, and Raman intense weak multiple bands. Okay, so this will be useful for them. And like I said, this is alpha helix, beta structures, random coils, amide 1, amide 2, and amide 3. So where you will get a peak. So this is just an example. Again, the same thing here. Yeah, so need not be same for all samples. So you may get a peak in 1500 region, and you will think that it is amide 1. But you will get the same peak when it is, when you run your sample of, vanadium or titanium. So you have to be why I'm saying is that you have to be very, choosy about how you are going to run the sample, and you have to know the history of your sample. You have to look into the literature, how previously people have done, how they got the results. So these things are very important. Okay. Yeah. So this is an particular important study. So I formed it in scientific reports, and what they have done is that they have taken fish samples, and they have run it in FDAR, and they have done a Pearson correlation coefficient to actually check the freshness of fish. So this particular study is there. Maybe you can just check. And this is a compound that we took spectra from in our lab. This is quercetin. And if you notice that there is a lot of peak in the fingerprint region, we call the 500 to 2000 region as a fingerprint region. You will see a lot of peak. Unlike other compounds, this particular compound will give you peaks like this. So if you're getting peak like this, then you can be sure that the purity is very high. If you are not getting a similar peak like this for this particular compound, then you have to check what exactly happened with the purity. Then maybe your sample is contaminated with other compounds, or the yield is not that great. So these things you have to look into it. Yeah, so this is another study that I've taken from this Journal of Food. They have taken the chemical composition of Atlantic bluefin tuna and Atlantic Spanish mackerel. So they wanted to actually check when the proteins rupture So that will give you an time frame of when it is actually the fish is spoiled. So it's basically how to detect the freshness of the fish. So if you see the peak here in amide 1652 region, and in the day one it is it looks after actually it's day 2, it looks good, and after day 12 there is a shift in the amide 1 and amide 2 region. So that can tell you an idea of whether the freshness is there or not. And this is another protein backbone assignment of the FTR spectra, amide 1 and amide 2. Similar for this is for silver carps. This particular study was done on 180 silver carps actually. So this is an interesting compound. This is Spectrin. Okay, so it's a marine natural compound, and the thing is, if you look into the structures, Spectrin, bromospectrin, dibromosceptrin, dibromosceptrin, so they all look the same, but with a small change in the bromine group alone. So you can do NMR to really assess the structure of the compound, but you also need the help of FTER in order to give you whether the aldehyde or ketone group is present or not, and the bromine group exactly where it is present. So that these things are very useful. FTER is very useful to detect the these compounds. And this is another study where extracellular polymers of biofilm forming bacteria, bacillus. So what happens with the polysaccharide extracellular polymers? So, and this is a shrimp shell that they have taken, and what happens is that they have used a salicylic for ionic liquid extraction. So they have done a time scan, and this is the spectra that they have obtained. This is another marine compound, Sinox. So it's basically azoledione, and this is how you get a spectra before and after the reaction. You get the isomer, and like this. So this is another spectra. So this is just a new study I've just taken. So this you can also do a time scan where you can see, if you look into this particular graph, the 0th minute there is no actual change. The reaction hasn't started. So that's the reason there is no peak in the 0th minute in the first here. And as time goes and the reaction has proceeded, you see a difference in the peak shift. You can see gradual increase in the peak intensity, and these particular groups can actually tell you so which are all the groups involved in the conversion of the adsorption of cellulose acetate. So and FTR is also used in authentication, detection of adulteration of food. For example, food adulteration is a major problem, and so you can see adulteration in orange juice and green tea and raspberry strawberry purees and vegetable proteins, and whey adulteration in cow milk. So these things, the technique that they have used is reflectance, and this I think I have obtained from a review article. So this data, so it is used there also. And this particular book was it is basically helpful for any biologist who is working on molecules, proteins, or someone. And this particular book, I found it very interesting. Maybe you can also take a look into it. Yeah, thank you so much for the opportunity. And if you have any questions, I'll be happy to answer.
Thank you, Karthik. Thanks for your presentation. Actually, I think Anjali is having some kind of internet issue. That's what we are unable to hear her voice.
Yeah, I cannot.
If there is any questions from the participant, you can use the right-hand option to interact with Dr. Karthik, or you can provide your queries in the chat box. That is the message you want to convey here. Anybody want to interact with Dr. Karthik? Okay, well, thank you, Karthik. Thanks for the presentation.
Thank you, sir. Thank you.